Okay, class, welcome back. And today we're going to do section 5. And this is going to be all about something called linear programming. And so linear programming is where you're given a system of equations, but they have a certain particular purpose, and it's basically, we call them constraints. And the idea is we're going to be maximizing or minimizing something. And this idea of finding a maximum or minimum value um, given these constraints is called linear programming. And we're going to talk about specific examples. But the objective is we're going to learn how to write an objective function. That's the function that we're trying to maximize or minimize. Um, how to use inequalities to describe the limitations in a situation. Those are called the constraints. And then we're also going to use linear programming to solve problems. And this comes up a lot. In fact, there's a class, um, finite math deals a lot with linear programming. Okay, so here we go. So a method for solving problems in which a particular quantity that must be maximized or minimized is limited by other factors is called linear programming. An objective function is an algebraic expression in two or more variables describing a quantity that must be maximized or minimized. So here is an example. So we have bottled water and medical supplies are to be shipped to to be shipped to victims of an earthquake by plane. Each container of bottled water will serve 10 people, and each medical kit will aid 6 people. So now let X represent the number of bottles of water to be shipped and Y be the number of medical kits to be shipped. Now we want to write the objective function that describes the number of people that can be helped. So we're going to call this the Z function. Okay, so Z is going to represent the number of people that can be helped. X is going to represent the number of bottles of water that can be shipped, and Y is the number of medical kits that can be shipped. So we need to figure out the combination of X and Y that will give us the maximum number for Z. So in this case, or the maximum number of people. So how many people can be helped with the bottle of water? Well, for every bottle of water, it's 10. So the number of people that can be helped, if we look at the number of bottles of water, okay, is going to be 10 times Y, or excuse me, 10 times X. And then since Y represents the number of medical kits, and we know that each medical kit will help aid 6 people, then we would represent the total number of people that can be helped with the medical kits as 6 times Y. And so if we put this together, we can write our objective function as 10x, which is the number of people that can be helped with the bottles of water, plus 6y, which is the number of people that can be helped by the number of medical kits. And so we want to find what combination of x and y that will make this number the greatest. And so this is going to be our objective function. Okay, and this is the function we're going to need to either minimize or maximize. And in this case, we want to maximize it. Okay. Yeah, that's all I want to say. Okay, so now a constraint is expressed as a linear inequality. Okay, it could be greater than, less than, greater than or equal to, or less than or equal to. So we list the constraints to form a system of linear inequalities. Remember, just like we talked about previously. So let's continue on with our example. So it says each plane can carry no more than 80,000 pounds. Now, the bottled water weighs 20 pounds per container, and each medical kit weighs 10 pounds. Let X represent the number of bottles of water to be shipped, and again, Y the number of medical kits. We want to write an inequality that describes this constraint. So, we know how many pounds each container of water weighs, and we know how many pounds each medical kit weighs. Okay, so we can set up a similar inequality like we did before. So what we're going to do is we take 20 times the number of containers of water, so 20 times X, and we take 10 times Y, and we add those up, right? And that can be no more than 80,000 pounds. So our constraint will turn out to be 20 times X plus 10 times Y has to be less than or equal to 80,000. And that's what we get. So this becomes one of our constraints. Okay. Now I hope this makes sense. Please study this and make sure you understand why this is a constraint. And so this is one of the constraints, or a constraint, that is limiting the number of bottles of water and kits that we can have. So this is going to be important to factor. We cannot ignore this. Okay, so now we're going to let z equals ax plus by be an objective function that depends on x and y. And then furthermore, z is going to be subject to a number of constraints on x and y. Okay, now, if a maximum or minimum value exists, it can be determined as follows. This is how you solve these. Okay, so what you're going to do is graph the system of inequalities representing the constraints. And then again, just like we did before in the previous section, you're going to graph the system of inequalities and shade in the solution region. Okay, and what we're going to call this is the feasible region. Okay, because the value that is going to maximize this objective function is going to be in the feasible region. Now, two, we're going to find the value of the objective function at each corner or vertex of the graphed region, what we call the feasible region. Okay, the maximum and minimum of the objective function must occur at one of the corner points, and this is by theorem. Again, this is not something we're going to discuss, I don't think, in this class, but it can be proved that the maximum and minimum value of the objective function must occur at one or more of the corner points. Okay, so guess what? That helps us limit the number of test points we're going to use, because each region, each feasible region that we're going to deal with is only going to have a certain number of corners that we can test. So we go ahead and test them all. So now what we're going to do is we're going to use the information, and we're going to determine how many bottles of water and how many medical kits should be sent on each plane to maximize the number of earthquake survivors who can be helped. So here's our objective function that we need to maximize. Here's the system of two equations. So let's see here, do they? Yeah, so they added another constraint. So we have these two constraints. So let's say we have these two constraints. So let's say the maximum number of people that can be helped, or excuse me, the maximum number of bottles of water that can be, let me rephrase that, sorry. The maximum number of containers that the plane will hold is going to be 6,000. So the sum of the number of bottles of water and the first aid kits cannot exceed 6,000. Okay, so it can only hold 6,000 items, and the weight restriction has to be no more than 80,000 pounds. So these are the constraints. So what does this mean? Well, we got to solve for this. We got to find the values of x and y that solve for this. So again, let's follow the steps. Okay, we're going to graph the constraints, the inequalities. Okay, so we're going to graph this inequality, and we're going to change it to an equal sign. So we're going to make it into an equation, just like we did before in the previous section. And we're going to then find the x-intercept, which is 4,000. And then we can find the y-intercept, which is 8,000, and then draw our line, right? And we do our test point, which again, the origin is a great one to use in this case. And so we get 0 is less than or equal to 80,000, which is true, which means we're going to be below, right? So here, there's our line, and we're going to be underneath, so we're going to shade below. Now, obviously, we're not going to go below x is equal to 0, right? It doesn't make sense to have negative bottles of water or negative number of first aid kits. So we're going to be only in the first quadrant. So that's another thing you can also always, in a lot of these problems, is x and y will always be greater than 0, or greater than or equal to 0, rather. Okay? So now, if we graph the other one, right? So we start with the inequality, change it to an equation, use the x and y intercepts to graph the line, and then use our test point, of course, to use the origin. And this is also true, so we're going to be below that line. So now, if we look at the regions, where do they overlap? They overlap right in here. So guess what our feasible region is going to be? Our feasible region is going to be right here. So this is going to be our feasible region. And so guess what points we're going to test? We're going to test, we need to find this point. We're going to test that one. That's the origin. We're going to find this point, right, which we know because it's the intercepts of this line here. So we know that one. Now this one we don't necessarily know because it's the intersection point between the two lines, but we can definitely solve for that. We've done that before. And then we've got this one. So these are our 4 test points that we're going to use. So how do we find this point? Well, we set these 2 equations equal to each other, and then we use either the substitution method or the elimination method to solve for x and y. So again, we can do that. And we can use those methods to find this point. So then we have all 4 of our points to test. Okay, and so here we go. So we multiply this by 10, or negative 10, right? And we get negative 10 here, and we eliminate the y's, and then we get 10x is equal to 20,000. And then we divide both sides by 20, or excuse me, by 10, and we get x is equal to 2,000, and then we back substitute. And if x is equal to 2,000, then y must be equal to 4,000, right? Because they have to add up to 6,000. So the number of bottles of water is 2,000. The number of first aid kits is going to be 4,000. Okay, so now we've got that other point. So now we've got this point right here. Okay, it's going to be 2,000 comma 4,000. And so now we just have to plug in each x value and see, we have to plug in each x and y value and see which one gives us the maximum z value. Okay. Okay, so now we're going to test the corner points. So here we go. So if we test 0, 0, well, what do we get? We get 0, right? Z is equal to 0. If we put in 4,000, comma 0, what do we get? We get 40,000. If we put in 2,000, comma 4,000, we get 44,000. And then if we put in 0, 6,000, we get Z is equal to 36,000. So look at here. So the maximum value for Z is right here, and that happens when the number of bottles of water is 2,000 and the number of first aid kits is 4,000. And so the number of people is maximized at 44,000 people when we can ship 2,000 bottles of water and 4,000 first aid kits. Okay, per plane. Okay, and that is the end of this section. So again, as I always tell you guys, please practice, practice, practice. Do the suggested homework. If you get stuck on the online homework or the projects, please reach out to me. We'll discuss this in class. Remember, in class is where we work and practice on the things like homework, suggested homework, projects, and just practicing what we're learning here on the lecture videos. But as usual, until then, have a great day.